Hello everyone, today our group will be presenting our project on risk-aware extensions to the TD3 algorithm. Specifically, we investigate two approaches, quantile regression TD3 and Gaussian TD3 that allows us to control the risk sensitivity of an agent in continuous control environments. Our group members are Anat, Uznik, Ruma, and this is myself, Singtek, presenting. Before diving into TD3 and our extensions, we'll briefly recap DDPG since TD3 builds directly on it. DDPG is an off-policy actor-critic algorithm for continuous actions. It uses a deterministic actor, where the policy outputs a single action, and a critic that estimates Q values. DDPG works, but it suffers from three major issues. 1. Overestimation bias from bootstrapping. 2. High variance TD targets, which cause unstable critic learning. And 3. High sensitivity to hyperparameters, which often leads to unstable trading. These weaknesses motivated the improvement introduced in TD3, which we'll cover next. TD3 improves on DDPG with three key stability mechanisms. First one is twin critics. TD3 uses two critics and takes the minimum of the Q estimates. This directly reduces overestimation bias. Next, we have delayed policy updates. The actor is updated only once every two critic updates, preventing noisy critic updates from propagating the policy. Lastly, target policy smoothing. Noise is added to target actions in the Bellman backup, which reduces sensitivity to sharp Q value spikes. Together, these changes make TD3 slightly more stable and sample efficient, and they deliver higher returns in mediocre environments. Our work extends the stable TD3 framework by making its value estimation risk-aware while keeping all of these stabilizing components intact. Before we introduce our methods, it's important to explain why risk even matters in reinforcement learning. A key insight comes from distributional RL, especially the QR-DQN work by Dabney. Their main finding is that the return in RL isn't just a single number. It's actually a full distribution with variability, asymmetry, and tail behavior. When we collapse that distribution into just a mean, like typical algorithms such as DDPG and TD3 do, we lose a lot of important information. The first issue is that averages high tail risk. Two policies can have the same expected return, but one might occasionally crash catastrophically while the other is consistently safe. Standard TD3 treats them as identical because it only optimizes the expectation. Next, risk-aware value estimation reveals the actual shape of outcomes. When the critic models a distribution or some form of uncertainty, we can explicitly see how often bad events occur and how severe they are. This lets us design agents that behave more conservatively or more aggressively depending on the task. Finally, all of this integrates seamlessly with TD3 because TD3's core stability mechanisms, twin critics, delayed policy updates, target smoothing remain intact. We only change how uncertainty is represented. So essentially, by learning quantiles of the return distribution, we give the agent access to the kind of information that average-based critics completely hide. Things like risk, uncertainty, tail events, and even potential multimodal outcomes. This becomes the foundation of our motivation to extend TD3 into a risk-aware algorithm. Before we explain our two methods, we also need to introduce the CVAR objective, since this is the risk measure shared by both QRTD and Gaussian TD3. CVAR, also known as conditional value at risk, let us optimize not for the average return, but specifically for the worst-case outcomes. The idea is simple. Instead of taking the mean of all predicted returns, we sort the critics' quantile outputs and look only at the lowest alpha fraction. Those represent the bad or risky scenarios. Mathematically, CVAR is just the average of those lowest quantiles. So a small alpha means we're focusing on more extreme failures, which corresponds to a stronger risk-averse policy. The actor objective is then to maximize CVAR, meaning we push the policy toward actions that perform well even in their worst-case predictions. QRTD3 modifies only the critic head while keeping the full TD3 backbone intact. Instead of producing a single Q value, each critic now outputs K quantiles that approximate the entire return distribution. The distributional view is what allows us to compute CVAR directly from the critic output, a key requirement for a risk-aware control. Architecturally, nothing else changes. Each critic is still a two-layer, 256-unit MLP, but the final layer produces K values instead of one. All TD3 stabilizing components, twin critics, delayed updates, and target smoothing remain unchanged. QRTD3 constructs the critic targets in a distributional way rather than using a single scalar. After computing the smooth target action, we evaluate both target critics and take their element-wise minimum to stay consistent with the TD3's conservative backup. From this minimum distribution, we build the Bellman target, which gives us one target sample for each predicted quantile. This is important. The critic is learning an entire distribution, not a single point estimate. So to train the critic, we use the quantile regression Huber loss. In practice, this loss is computed pairwise between every predicted quantile and every target sample, which approximates the one Wasserstein distance and ensures that the critic learns a coherent distributional representation. Now I'll explain our second method, the Gaussian TD3. Gaussian TD3 keeps the exact TD3 architecture, twin critics, delayed actor updates, and target policy smoothing. The only change is how the critic represents uncertainty. Instead of predicting k quantiles like QRTD3, the critic in Gaussian TD3 predicts a normal distribution over returns. So the critic now outputs just two numbers, a mean value and an uncertainty term. This makes the representation far simpler and cheaper than learning k quantiles. Just like TD3, we use the minimum of the two target critics to reduce overestimation. Notice we only use the mean from the target critics. Variance is learned only on the current network. Because the critic model is a Gaussian, we train it by maximizing the likelihood of the Bellman target under the predicted normal distribution. This loss encourages two behavior. One, the mean should match the Bellman target, and two, the variance should grow when the target is noisy and shrink when predictions are confident. To compute CVAR, the actor needs samples from the critic distribution. We generate these environments using the reparameterization trick. This lets gradients flow through both mu and sigma so the policy can learn how to manipulate risk. And we sort the sample returns and take the lowest alpha fraction of them and maximize their average. This directly optimizes for low returns performance in making the agent risk averse or risk seeking depending on the alpha value. Overall, Gaussian TD3 gives us a lightweight, smooth distributional critic that is easier to train than QRTD3 while still enabling CVAR-based risk-sensitive control. Before comparing our algorithms, we standardized the experience settings across all methods. We used the official TD3 hyperparameters to ensure fairness and train everything with 5 random seeds to report stable averages and standard errors. We follow a stage evaluation procedure. First, tuning the risk parameter alpha for Gaussian TD3, then tuning the number of quantiles k for QRTD3, and finally running a full comparison across 7 MuJoCo environments. Certain MuJoCo environments behave very differently in terms of risk. Walker 2D and Hopper are classic examples where the small control errors can cause catastrophic fails, creating extremely high downside variance. These environments reward stable behavior, so tail outcomes really matter. To contrast this, we also include inverted double pendulum, which almost never has catastrophic failures. This let us test how risk-aware methods behave in both high-risk and low-risk setting. Here's, Here we're looking at the Gaussian TD3 ablation over different alpha values. Alpha directly controls how risk-sensitive the CVAR objective is. Small alpha makes the policy more risk-averse, while larger alpha makes it more risk-seeking. We tested alpha values from 0.1 up to 0.9 and across all environments, and the most consistent and highest performing setting was when alpha was set to 0.75. This result actually makes sense when we consider TD3's architecture. TD3 is already fairly conservative due to the twin critics and the minimum operator, which bias the value estimate downward. So giving the actor a slightly risk-seeking CVAR target helps to counterbalance that conservatism, producing better overall performance. Because of this, we fix alpha to 0.75 for all remaining Gaussian TD3 experiments. For QRT3, we next tune the number of quantiles k. Higher k gives a richer distribution, but also increases variance in computation. Across tasks, there's no single best k, but we choose k to 10 since it provides improved performance on both Hopper and inverted double pendulum. However, across all values of k, QRTD3 does not outperform TD3 on Walker. This suggests that modeling the low return tail more accurately requires slightly higher distributional fidelity, so we choose k to 10 for the remaining experiments. In the final comparison, Gaussian GD3 performs the best overall, achieving the highest return in 4 of the 7 environments and a strong second place in several more. We attribute this to the inductive bias of Gaussian critic. Many MuJoCo returns are unimodal and smooth, so a simple parametric distribution prevents overfitting and gives the actor a cleaner learning signal. QRT3 is more expressive and can model complex distributions, but this flexibility also introduces more variance, making it less stable in limited data regimes. Overall, Gaussian TD3 offers the best balance between expressiveness and stability. Here we summarize learning curves across all environments to visually support the claims we made earlier about the risk-aware TD3. First, across most high-variance environments like Hopper and Walker 2D, you can see that the Gaussian TD3 consistently converges faster and more smoothly. The curves show lower variance between seeds and fewer oscillations, which aligns with our explanation that the Gaussian critic acts as a regularizer by smoothing the return landscape. QRT3 generally performs well, but shows higher variance between seeds and occasional instability. This matches the idea that a flexible quantile distribution can overfit to noisy off-policy data, especially when the real return distribution is unimodal. So in simple, low-risk tasks like inverted pendulum, all algorithms perform similarly, and Gaussian GD3 does not provide much advantage, which is actually expected since the underlying return variance is small and distributional modeling adds unnecessary overhead. Finally, across the majority of environments, Gaussian GD3 either outperforms or matches GD3, supporting the main claim that adding risk sensitivity improves stability and robustness without changing the GD3 architecture. To wrap up, our project introduced 2 risk-aware extensions to GD3, QRGD3, and Gaussian GD3, both of which allow us to control an agent's risk sensitivity using CVAR. From our experiments across 7 environments, we saw that risk awareness can significantly improve performance, especially in high-risk tasks where rare catastrophic failures dominate learning. Gaussian TD3 in particular performed the best overall thanks to its strong inductive bias, which stabilizes training and reduces overfitting. But we also encounter several challenges. QRTD3 is highly expressive, which means it can overfit noisy off-policy data when samples are limited. Gaussian TD3, while stable, becomes restrictive when the true return distribution isn't well approximated by a single Gaussian, especially in multimodal or adversarial settings. And in simpler environments with almost zero variance, both methods add unnecessary optimization overhead. And basically, you're learning variance or quantiles even when they don't matter. So overall, our study shows that adding risk awareness to TD3 does improve robustness and performance, but the choice between Gaussian and quantile critics depend heavily on environment complexity. These insights motivate future work, such as adaptive risk scheduling or hybrid models that combine Gaussian stability with quantile flexibility. For future work, there are a few exciting directions we think are worth exploring. First, we want to apply the same CVAR-based actor update to the DDPG algorithm, since DDPG doesn't have TD3's conservative twin critic architecture. It tends to suffer more from overestimation, so using a more risk-averse alpha might be necessary to stabilize training. Next, it will be very interesting to evaluate these risk-sensitive methods in environments that are inherently multimodal or even adversarial. These settings often have complex and deceptive reward landscapes, which would challenge both Gaussian and quantile-based critics in different ways. Another promising idea is adaptive risk scheduling. Instead of keeping alpha fixed, the agent could start training with a more risk-averse policy and then gradually shift toward risk-neutral or even risk-seeking behavior as its performance improves. We also think it would be valuable to explore richer distributional forms beyond the Gaussian assumption. For example, mixture models or heavy tail distribution could capture more complex return structures while still preserving some of the stability benefits we see in Gaussian TD3. Finally, a very important direction is to go beyond reward as the only evaluation metric. For safety critical applications like robotics, autonomous vehicles, or healthcare, we need metrics that explicitly measure safety and alignment. Testing these algorithms under those criteria would tell us much more about their suitability for real-world deployment. Overall, we believe the risk-sensitive perspective opens the door to a lot of promising research, both algorithmically and in terms of practical impact. Thank you.